All right, so we've talked about single slits, we've talked about double slits. Last thing we have to do with interference is talk about diffraction gratings. And so a diffraction grating is basically anything that's more than two slits, right? So here's my light coming this way, and it's got some wavelength, right? And now there's 4 openings. And so we've looked at what happens with a single slit and a double slit, and it's the same concept, right? So I've got a screen over here, and the screen is some distance L away. That hasn't changed, right? Wavelength hasn't changed. But what you're going to see when you shine light through a diffraction grating is you're going to see a pattern that has multiple bright spots that are spread out kind of evenly. So it's going to look something kind of like this. There's a bright spot here, and then there's some little spots here, and there's another bright spot, and there's some little spots, and then there's the central maximum. There's always going to be a central maximum, and then there's like another bright spot and another bright spot. So you get these bright spots at these points, right? So again, M is where your bright spots show up, right? So this would be like M equals 0. This would be M equals 1. This would be M equals 2, right? So again, here's M equals 1. Here's M equals 2. So you get these bright spots that show up, but you get these little spots in between where you're not having as much interference. The intensity is less. And so real quick, look at what's happening. We already know how the central maximum is formed, right? Because everything travels the same distance. So let's look at like a point up here, like M equals 2. So this light, all these points have some light traveling up at an angle to get to M equals 2, right? So each one is going to be a little bit different. So if I draw a line straight down, kind of like I did before, from here, there's a path difference right there. And then over here for this one, same thing. There's a path difference here. Same thing for the next one. This little thing right here, there's a path difference. So each of these things, when they're going to like the M equals 2 point, or the M equals 1 point, or the ones down here, right? If you have this path difference, the distance that the one below it has to travel further to get to the same point, if it's a whole multiple, just like before, whole multiples give you constructive interference, half multiples give you destructive interference, and you get the same kind of constructive-destructive pattern. So this is with 4 slits, right? But it could be 5 or 6 or 10 or 100 or 1,000. And the interesting thing is all of these patterns we looked at all come from the single slit pattern. So here's what a single slit pattern looks like. A double slit pattern follows the same basic shape, but because there's 2 openings, there's more opportunities for interference. If I change to 3 slits, now it still looks like a double slit, but there's a small maximum in between each big maximum where the intensity has gotten small. If I make it 4 slits, same shape, except now the big maxima get a little sharper, and there's 2 dim spots between each big bright spot. And so you can see this pattern repeat. Each time I add a slit, the big bright spots get more focused. So the more slits I have, the more precise I can measure the spacing. Look at the difference here between 5 slits and 500 slits. More slits makes my lines sharper and easier to measure. This is why we use diffraction gratings instead of double slits when we do spectroscopy, which is something we're going to get into later on. Okay, so let's look at how to solve some diffraction grating stuff. So same equations apply from single slits and double slits, right? Except some of these things are going to mean different things, but it's still the same equations, right? And so this is important. Double slits, you could look at either bright spots or dark spots, right? Depending on if M was a whole integer or a half integer. So double slits are kind of like the baseline. You can go either way. You can look at dark or you can look at bright. Single slits, remember we said M was the dark orders, the dark fringes. It's opposite for diffraction gratings. So for diffraction gratings, we care about the bright spots. We don't care about dark spots. We only care about bright spots. Okay, so same equations. So, but in this case, M is going to be your bright fringe order, right? Bright fringes, not dark fringes. And then theta is going to be the angle between bright spots, and D is going to be, instead of the distance between slits, it's going to be the distance between each consecutive slit, right? So there's more than one slit. So it's kind of like double slits, but it's there's multiple slits and each slit should have the same spacing. So it's distance between the slits. And another number you'll see a lot is the number of lines per unit, right? So N is the number of lines per distance, right? So like for instance, 10,000 lines per millimeter, right? I can get D from knowing that number. So if I know, let's say there's 100 lines, if I have 100 lines per centimeter, I know that 1 centimeter has 100 lines. So if I just take the reciprocal of that, that would tell me how many centimeters is 1 line, right? So if I have the number of lines per unit distance, then D is going to equal 1 over N. So 100 lines per centimeter is going to equal 1/100th centimeters for every line. Okay, let's do some practice problems real quick. First one, a diffraction grating has 2,000 lines per centimeter. Calculate the angle for the first maximum with 520 nanometers light. So again, this is going to have angle, so I'm using m lambda equals d sine theta. So first, I need to get d. So my number of lines is 2,000 lines per centimeter. So that means that d is going to be 1 over 2,000. And so 1 over 2,000, that gives me 5 times 10 to the minus 4th centimeters, but I need to turn this into meters. So that's 5 times 10 to the minus 6th meters. Okay, now I can plug in and solve. So m lambda equals d sine theta. So that means that theta is going to be the inverse sine of m lambda divided by d. I'm going to divide the d over, right, and then take the inverse sine. So that's m lambda over d. So that's the inverse sine of m is going to be 1, and my wavelength of light is going to be 520 times 10 to the minus 9 over d, which is 5 times 10 to the minus 6th, 5 times 10 to the minus 6th. And so if I do this, you should end up with 5.97 degrees as the angle between those two. Okay, second one. Diffraction grating has 10,000 lines per centimeter. Calculate the wavelength of the light if the third maximum is at 25 degrees. So same thing. So let's start. N is 10,000. So D is 1 over N. So that's 1 over 10,000. And if I do that, that gives me 1 times 10 to the minus 4th centimeters, which is 1 times 10 to the minus 6th meters. That's my D. Now I can solve. So m lambda equals d sine theta. We're going to solve for lambda. So lambda is d sine theta over m. All right, and so d is 1 times 10 to the minus 6th times the sine of my angle is 25 degrees over, let me draw a line here, over m. I said third maximum. Third maximum, my m is going to be 3. And so if you do this, you get a lambda of 1.41 times 10 to the minus 7th meters, or 141 nanometers, which kind of makes sense. All right? Okay, so diffraction grating problems, if you can do double slits and you can do single slits, you can do diffraction gratings. We just have to redefine what these things mean, but it's the same basic equations.